Good good morning and welcome back. We are in the back half. We're on the finishing line. We are almost done with this year. I know this last 2 months have dragged on and on and on and on, but we are almost there. So, let's talk about our last topic for the year. This is the last topic. Get through this topic, we're done. That's it. So, what is the topic? The topic is gas laws. So, we're going to talk about gases, how they react, how they behave, why they react to behave that different way. Um, and just talking about a few certain laws that you need to know moving forward in your life. So, let's get into it. So, what are gases? That's probably a good thing to define when you're talking about gas laws. Gases are a state of matter that have variable volume and shape, meaning that there is no set volume, there is no set shape. They take the shape of their container. Same with volume. They expand to occupy all the volume available. So if you put a small amount of gas into a large vacuum, it will expand to take up the entirety of the large vacuum. For gases, volume, pressure, temperature, and the number of moles present are interrelated, meaning that if something happens to one of them, it's going to affect the other three. So if something happens to volume, pressure, temperature, and number of moles are going to be affected. If something happens to the number of moles, volume, pressure, and temperature are going to be affected. Those three are all interrelated in different ways. So we're going to talk about those. That's what most of our gas laws are going to be. They can be very easily compressed. In fact, they can be compressed to the point where they actually will turn into a liquid. But they can be compressed fairly easily. If you don't believe me, press down on your tires on your bike or on a balloon. Very easily compressed. They exert pressure on whatever surrounds them. That's actually how some people measure gases. If you've ever heard of PSI, that's pounds per square inch. That is measuring the gas pressure or the air pressure in your tires. And they easily diffuse into one another, meaning that they easily mix. They don't just stand, oh, this section is oxygen, this section is nitrogen. No, they very easily mix and intermingle. So, we're going to talk about the kinetic molecular theory. So, the theory of moving molecules. What it basically says is that matter consists of particles, so anything that consists of atoms or molecules are always in motion. And that the volume occupied by gas particles is has a negligible small effect on the behavior, meaning that it's not going to really affect how they react, how they behave. Collisions between particles are elastic, meaning that they're kind of like the pins of not the pins, the balls when you're playing pool or 8-ball. You hit the white ball, it smacks into the other ball that you're hitting, and they bounce back together equally. That's what elastic means. It means that they bounce perfectly. Uh, there's nothing stopping them. There's nothing slowing them down. They just bounce and keep going. Attractive forces between particles are negligible meaning that they don't really exist. For our purposes, we're going to say that basically gases do not react with each other. That's the basics of it, is that when we talk about gas, it's not going to have a reaction. It's not going to have anything that makes it slow down. It's just going to be what it is. Now, that's not completely accurate, of course. That's going to be some leeway between that and what is going to be reality of it. However, for our purposes, this is some of the assumptions that we're going to make. Gases have no fixed volume or shape, but take the volume and shape of the container. Okay, we just talked about that. And that the average kinetic energy of the particles is proportional to their temperature in Kelvin. That's very important because Kelvin doesn't have a negative portion to it. It's only going to be positive. Since it's going to be positive, we have to have all of our temperatures in Kelvin. So, make a little note of that right now. All temperatures must be in Kelvin. Can't be in Fahrenheit, can't be in Celsius, has to be Kelvin. So, our first of our gas laws is called Boyle's Law, named after Charles Boyle. What his law states is that the pressure and volume of a gas are inversely proportionate at constant pressure, meaning that if you were to increase the pressure of something, that likely means that you're going to decrease the volume. So if you decrease the volume of something, you're going to increase the gas pressure inside of it. You push onto a car tire, it's going to actually increase the pressure that you're feeling. If you decrease the pressure, the volume is actually going to be increasing. It's one of those weird things. So pressure goes down, volume goes up. Volume goes down, pressure goes up. That's the basics of what you need to know. If you look, a graph of pressure and volume gives you an inverse function, meaning that it looks something like this. A graph of pressure and the reciprocal of volume gives a straight line. So, if we take the reciprocal of the volume and the pressure and graph them out, we'll have a straight line rather than this curve that's right here. Here is a sample problem. P1 V1 is equal to P2 V2. So pressure 1 times volume 1 is equal to pressure 2 times volume 2. They took 210 kPa, that's right here, times 4 centimeters cubed, that's our volume. What will the pressure be at 2.5 centimeters cubed? 2.5 centimeters cubed is our pressure, divided over, and you get 340 kPa. These are very simple equations, usually just one move, one division, one multiplication, and that's all you really need. So, these are not too difficult. We should be able to do them fairly easily. So after Boyle's law is Charles' law. According to Charles' law, the volume of a gas is directly proportional to the Kelvin temperature as long as the pressure is constant. Meaning that as the volume goes up, so does the temperature. As the temperature goes down, so does the volume. So volume up, volume down, temperature down. The temperature of gas laws must be expressed in Kelvin. So it's a very important point. It has to be in Kelvin, where Kelvin is equal to whatever degrees Celsius they give you plus 273. We're not going to care about the 0.15. It's just plus 273. So make sure that you know that. Do not take a Celsius and plug it into the equation. That would be wrong. You need to have Kelvin. So the graph of temperature and volume gives you a very nice straight line because it is directly proportionate. Where you see the x-axis is defined as absolute zero. Absolute zero is when all motion stops. We're not really going to get into that too much right now, but make sure that you know that at this zero temperature and zero volume, that is known as absolute zero. So we have our sample problem here. A gas sample at 40 degrees Celsius occupies a volume at 2.32 centimeters cubed. If the temperature is increased to 75 degrees Celsius, what is the final volume? So we have V1 T1 is equal over T1 is equal to V2 over T2. We have to convert the temperatures to Kelvin. So we have 40 degrees Celsius and 75 degrees Celsius. Both of those we're going to add 273 to get Kelvin. So 40 plus 273 is 313. And then 75 plus 273 is 349. So all I had to do, move it over, and get 2.58 should be centimeters cubed. So 2 gas laws down, 2 to go. We are halfway there. So we had Charles' law, Boyle's law, now we have Gay-Lussac's law. Gay-Lussac's law defines the relationship between pressure and temperature of a gas. It's basically saying that the pressure and temperature of a gas are directly proportional. So just like volume and temperature, however, in this case, it's pressure and temperature. So it's P1 over T1 is equal to P2 over T2. So they're directly proportional. So when something is being divided by something else, those two things are directly proportional. If they're being multiplied, they are inversely proportional. So, sample problem 3, The pressure of a gas in a tank is 3.2 atmospheres at 22 degrees Celsius. If the temperature rises to 60 degrees Celsius, what will be the pressure in the tank? So for Gay-Lussac, we have pressure and we have temperature. Since we only have a pressure and temperature here, we're going to go ahead and plug them in. So P1 over T1 is equal to P2 over T2. Our first step is going to be convert our Celsius into Kelvin. So convert the temperature of Kelvin, 22 degrees Celsius plus 273, 295. 60 degrees Celsius plus 273, 333 Kelvin. So then we just have to plug everything in, plug and chug, 3.2 atmospheres over 295 Kelvin is equal to P2 over 333 Kelvin. You multiply it all out and you should get that answer of 3.6 atmospheres. Try this out for yourselves, put it on your notes, and see how you do. Make sure that you stop at each of these. I know I'm going kind of fast, but make sure that you're stopping and taking the time to actually try these sample problems out for yourself. Finally, there's Avogadro's law. Avogadro's law talks about the equal volumes of gas under the same temperature and pressure contain the same number of molecules. What he's basically saying is that when volume is the same, when you have the same temperature and pressure, that's when you know you have the same number of particles or same number of moles. If the temperature and pressure are constant, the volume of the gas is proportional to the number of moles of gas present. So what that basically means is V is equal to, the volume is equal to a constant times N. Or, in easier terms, V1 over N1 is equal to V2 over N2, where N is the number of moles of gas. Small n is always going to represent number of moles, not necessarily of gas, but always number of moles. So if you see a small n in any science equation from now until eternity, it's going to stand for number of moles unless someone else starts doing some weird stuff. So we have V1 over N1 is equal to V2 over N2. So when temperature and pressure are constant, you're going to have volume and number of moles. So if you see it ever give you a problem where you're having number of moles and a volume, that's when you know you're going to use Avogadro's law. And you're going to use it just like you would Gay-Lussac's law or Charles' law. So finally, we're going to identify an ideal gas. So in an ideal gas, it basically follows the laws of the kinetic molecular theory. So particles are in continuous, random, and rapid motion. Particles collide with no loss of momentum, meaning that they're not slowed down at all. Volume occupied by particles is essentially zero when compared to the volume of the container, so they're incredibly small. Particles are neither attracted to each other nor repelled, so they're just kind of hitting each other, and that's it. The average kinetic energy of the particles is proportional to their Kelvin temperature. Basically, their energy is defined by their temperature. At normal temperatures and pressures, gases closely approximate ideal behavior, meaning that usually, under normal circumstances, these are mostly true. Not all of them. They're not all of them completely true. None of them are true 100% of the time, but they're true enough that we can make these assumptions without being too far off in our actual data. So, these are the types of assumptions that we have to make as scientists because, frankly, we cannot take into account all the exceptions to these rules as we go. We just got to do what we can to deal with the exceptions on a case-by-case basis. So that is actually it. We have gone through the entire notes cycle. Please make sure that you're going through this and checking yourself throughout this. I did go rather quickly throughout the examples and samples. Please make sure that you go through and listen again. If you need any help, if you need extra help, if you have troubles getting on to any of the homeworks for this week or past weeks, please make sure that you're contacting me through email or some other type of service. And please, for the love of all things holy, please make sure that you are getting all your work in by Monday at noon. That is when things are due. That's when I have to record whether or not you were present for this week. In the meantime, stay safe, stay indoors, and stay healthy.